Welcome to theastrodynamics.com and theastro.com. This website promotes the right way to build a commercial space catalog. I am Jim Durr. I develop computer codes for rapid and automated space catalog building. This website has many self-contained videos for catalog building. If you are familiar with any of the topics, you may skip to other videos of interest. Rapid commercial space catalog building is the key to space domain awareness, SDA, around the Earth. The analytic algorithms for this space catalog are using Earth-centered inertial (ECI) state vectors, unlike the two-line element TLE catalog of the US Air Force. Before discussion of how analytic astrodynamics orbit determination algorithms are used to build a space catalog, preliminary understanding is needed on three topics. 1. Analytic perturbed orbit propagators. 2. New SP-type space catalog. And 3. Processing millions of optical and radar observations per day. The first video of this preliminary topic, analytic perturbed orbit propagators, are originally and independently developed by Bauer and Winty in 1959 for rapid space catalog building. Again, if you are familiar with the three preliminary topics, you may skip to the videos of track association, also known as correlate observations, initial orbit determination, IOD, and differential correction, DC. In 1959, Bauer and Winty invented independently analytic perturbed orbit propagators A and B respectively, which have been developed further into the HB4 and Winty algorithms. The TLE space catalog contains known objects with mean orbital elements in the TLE. Therefore, the combination of TLE HB4 can only process known objects for catalog maintenance. Unknown objects, or UCTs, have no TLEs until after successful UCT processing of observations of the unknown objects to produce new or candidate ECI state vectors of the unknown objects, and then TLE conversions if desired. Therefore, the combination of SP Winty can process both known and unknown objects for both catalog maintenance and catalog building. In astrodynamics, there are only two analytic perturbed orbit propagators, Bauer HB4 and Winty. The choice of analytic perturbed orbit propagators is fundamental to catalog maintenance and catalog building. Observation processing for cataloging requires only perturbed orbit propagation for short duration, at most 1 or 2 days. The Bauer or HB4 propagator is a good algorithm for catalog maintenance and track association, but no use for UCT processing, since UCT is an unknown object without a TLE. If UCT processing cannot be processed accurately, then the choice of HB4 leads to good performance for primarily catalog maintenance. Extending HB4 for long duration orbit propagation has nothing to do with catalog maintenance and not helpful for catalog building. The Winty propagator, which has been neglected by the US Air Force, US Space Force, and astrodynamics researchers for decades, can perform analytic perturbed orbit propagation for both track association and UCT processing for known and unknown objects. The input and output of Winty propagator are ECI state vectors, and there is no need for a known TLE. The choice of Winty leads to better performance for rapid catalog maintenance and catalog building in terms of ease of use, accuracy, and robustness. Over 6 decades ago, the U.S. Air Force Astro Standard chose the HB4 orbit propagator and the two-line element TLE to build the TLE space catalog for rapid catalog maintenance. The combination of TLE HB4 works well only for known space objects, as in box 1, correlate observations, also known as track association as indicated by the blue arrow. Before UCT processing, unknown objects or uncatalogued targets, UCTs, have no TLEs. UCT processing is forced to use inaccurate two-body orbit propagators in box 2 to deduce inaccurate state vectors and converted TLEs of new objects, hoping that future pointing will reacquire the new objects again. Also, dense observations are collected in order to minimize errors due to two-body orbit propagation in UCT processing. Therefore, the use of HB4 is primarily for correlate observations. The consequence is decades of catalog maintenance and efficient, time-consuming catalog building, as indicated by the red broken links. The choice of TLE HB4 plus two-body orbit determination in UCT processing also generated a misunderstanding or confusion between track association and UCT processing. Track association starts with known TLEs or state vectors, while UCT processing starts with given observations. Track association output computed observations to be compared to the observed or given observations, while UCT processing aims to output IOD and DC state vectors. The confusion: track association may output probabilistic data suggesting multiple hypothesis theories, since the observed minus computed observations may be probabilistic with unknown errors. However, IOD and DC in UCT processing are deterministic with or without successfully deducing any state vectors. Again, TLE HB4 plus two-body orbit determination in UCT processing lead to inaccurate state vectors and, in turn, difficulties for catalog building and poor space domain awareness (SDA) performance. After about year 2020, the rapid increase of small satellites is mostly in the low Earth orbit regime, LEO, with approximate altitudes between 150 to 2,000 kilometers, depicted by the white wing. Today, tracking LEO objects for cataloging are mostly using numerous ground-based government and commercial optical systems worldwide. Radar systems are too expensive if costs of building, operation, and maintenance are included. The use of space-based optical sensors for cataloging has yet been implemented quickly due to hardware, software, and economic difficulties. About 90% of the space objects around the Earth are in the LEO regime. For short-duration orbit propagation, WINDY is more accurate than HB4 in general. If you think this is a biased opinion, it is. However, it is easy to make a comparison using a one-day TLE or SB space catalog. Note that Jim De is the student of Professor John Windy at MIT, and he inherited the research works and documents of Windy. See historical details at the PDF document, Bauer versus Windy. Also, he provided the source code of the first working Windy algorithm, Windy 6, included in the Windy's 1989 AIAA book, Orbital and Celestial Mechanics. Note also that Jim De's PhD thesis advisors at MIT are Ted Edelbaum and Dick Batten. For catalog maintenance and catalog building, observations are usually collected and processed in short time duration within 1 day. That is, orbit propagators are needed in track association and orbit determination, IOD and DC, in UCT processing. Again, in year 2024, at least 90% space objects are in the LEO regime. This picture depicts the accuracy comparison of a LEO object, a global star satellite at altitude of about 1,500 kilometers, in terms of position difference of 4 analytic orbit propagators against GPS reference data. The larger figure shows the position difference of 0 to 20 kilometers, where Windy in red outperforms HB4 in green, AGI Secular J2 in pink, and two-body in black for the LEO short duration orbit propagation of less than 3 days. An unbiased accuracy comparison should use a 1-day TLE or SP space catalog with at least 10,000 objects. Analytic versus numerical orbit propagation and CPU timing comparison. Input-output, two-body Kepler, Windy, and numerical integration are ECI state vectors, but HB4 uses known mean orbital elements in TLE as input and ECI state vector as output. Applications: two-body Kepler, Windy, and numerical integration can be used for satellites and missiles, but HB4 can only be used for satellites. Efficiencies: two-body Kepler, Windy, and numerical integration are efficient for known and unknown objects, but HB4 can only be used for known objects. For short duration orbit propagation, Windy and HB4 can compute a trajectory in a few microseconds on an Intel i3 processor and sub-microseconds on an i7 or i9 processors. This picture shows the advantages of Windy over HB4 in speed, accuracy, robustness, simplicity, and flexibilities. For short duration orbit propagation and over 90% of the space objects around the Earth, perturbations of J2, J3, and most of J4 are more than accurate enough for track association, IOD, and DC. Perturbation of the Sun and Moon can be included in the last iteration of DC if needed. If parallel processing is desired, use of HB4 is problematic since TLE conversion may or may not be successful. The long history of Windy algorithm code developments started as Windy 1 in 1963 and ongoing to Windy 8 in 2023. The Windy 6 source code included in my book, Analytic Astrodynamics Algorithms for Rapid Space Catalog Building, is the latest version of Windy 6. Windy 7 improves the robustness. The Windy 6 and Windy 7 algorithms can compute about 200 accurate trajectories per second on an Intel i3 processor in 2010, and over 1 million accurate trajectories per second on an i7 or i9 processor in 2023. Windy 8 is not needed for short duration orbit propagation as needed for catalog building. Windy 7 has been flight tested in CubeSats Proxima 1 and 2 in 2018. To get a state vector, Windy 7 uses 1 to 3% of electrical power compared with that of a GPS lock, and the precision error is less than 2 kilometers per day. For a state vector update between two GPS locks, the use of Windy 7 incurred insignificant precision error. but much needed electricity saving for QSAT operations. The first consideration of IoT and DC algorithms is the choice of the Winty algorithm for analytic perturbed orbit propagation. Analytic perturbed orbit propagators, SGB4 and Winty, can be used for track association or correlate observations in Box 1, SP-type space catalog, or SP for short, can be constructed with the use of Winty and/or numerical integration for UCT processing in boxes 2 to 7. Note that numerical integration with desired perturbations may be used for the last iteration of DC in boxes 4 to 7 if needed, for example, for lunar trajectories. This picture shows that accurate observations and analytic perturbed orbit propagators lead to accurate IoT and DC, and in turn, accurate catalog building and space domain awareness (SDA). In 2023, many commercial space companies can build a SP or SP-type space catalog with the goal of automatic catalog building. If Winty is used, the accurate state vectors in SP can be used directly for analytic perturbed orbit propagation in boxes 1 to 7. However, if SGB4 is used, analytic perturbed orbit propagation can only be used in box 1, since UCTs have no TLEs before IoT and DC. Of course, the accurate state vectors in SP can be converted to mean orbital elements as TLEs. However, the TLE conversion and SGB4 are not robust, making automatic catalog building difficult. Del Astro promotes new analytic perturbed algorithms for automatic commercial space catalog building. This website is not funded or supported by or related to any government. The opinions expressed in this website are purely based on decades of research. Again, this website promotes an alternative method for efficient automatic commercial space catalog building. This video discusses the first consideration of track association, IoT and DC algorithms, the analytic perturbed orbit propagators. Today, many commercial space companies claim that they are building their commercial SP space catalogs. However, if they are using SGB4 for analytic orbit propagation in track association, conjunction, and collision analysis, they are also building their second TLE space catalogs. That is, they converted the accurate state vectors in the SP into mean orbital elements in the TLE. It is well known that this conversion is not robust, and SGB4 has singularities, and in turn making automatic catalog building difficult. On the other hand, the analytic SP Winty method improves efficiency by using directly the accurate state vectors in the SP space catalog for analytic orbit propagation in track association, UCT processing, conjunction and collision analysis, prediction for future pointing, among others. That is, instead of building two catalogs, SP and TLE, only the SP catalog is sufficient for catalog maintenance and catalog building, not to mention the problematic TLE conversion, and the use of SGB4 becomes redundant. Also, the SP Winty method provides not just a second opinion to the TLE SGB4 method, but improves and verifies other computer results. To conclude this video and make further videos for space catalog building, your comments and critiques are welcome. Coding the equations of theories is much more complicated in the real world. That is why the source codes of astrodynamic algorithms are missing in most textbooks, let alone analytic perturbed algorithms, and real-world numerical examples for space catalog building. This is no knock to many excellent textbooks. My two motivations: 1. Supplement textbooks with concise theories and coded algorithms. 2. Provide key analytic algorithms for rapid commercial space catalog building with source codes in Fortran, C, or MATLAB, and over 100 real-world numerical examples. Thanks to the endorsement by David Golado, the topic of fast and accurate whole catalog SSA or SDA is important, challenging, and seldom discussed in detail. This text provides a foundation from which a SSA system can be built. Jim's use of Winty propagation makes it even more interesting. I am Jim De. My book may help a student to ace a course or shorten the learning curve of a master's or PhD thesis topic of astrodynamics, orbital and celestial mechanics. Also, the concise theories, key equations, source codes in Fortran, C, or MATLAB, and over 100 real-world numerical examples may help practicing engineers and scientists to develop new ideas and insights to solve today's problems. Thank you for watching this video of theastro.com.